arc length on a polar curve. So we're going to approach this exactly the same way as we did arc length on a parameterized curve. So that was arc length was from the parameter t from a to b of the magnitude of the speed, that was the velocity vector's magnitude, times the change in t, dt. And when you add that up, you had distance. So just to remind you, velocity or distance is a velocity times the time, basically. So that's why, if you're trying to find a total distance, you should be adding up velocities times time increments. Okay, so now to our problem. We want to do it for a polar. So what we do is take our polar, so this is like r equals 1 minus cosine theta, any kind of function of theta there. The parameter is just theta. I mean, we know it's an angle, but really it's just a parameter. And of course our definition of x is r cosine theta, because the definition of cosine theta is x over r. So that's where it comes from. So r is just a function of theta, so that goes in here. And similarly, y is r sine theta, and of course the r is the function of theta. So then, with those definitions, you have the parameterization with coordinates x of theta, y of theta, very similar to x of t, comma y of t, and there has to be a range of values, and that's from angle alpha to beta, but really it's just a parameter alpha to beta. So that's the parameterization, and of course this is the vector form of that parameterization. So therefore, the arc length on a polar curve, defined this way, from alpha to beta, is this formula right here, and that looks exactly, that is the parameterized form for the arc length of a parameterized curve. Okay, so here's an example. Find the arc length of r equals cosine theta from theta equals 0 to pi. So now, why is it only pi? Well, I graphed this in a wind plot, and I just did 0 to pi, didn't go all the way around to 2 pi. It rendered the entire circle. And that's because if you plot some points for thetas into r cosine theta, you'll see that it finishes out one version of the curve for theta equals 0 to just pi. If you go to 2 pi, you would have traced the circle twice. So I just want to go around once, because I just want to see the arc length on that circle. So we go over here, and I showed this on another video, but for that particular form here, r equals cosine theta, you have your r is the cosine theta, and your r is the cosine theta. So when you work those out and take the derivative, you're going to get this for the x prime, and on a previous video I showed that this product rule would come out to be cosine squared minus sine squared. So then just plug into the arc length formula. You just do x prime of theta squared, y prime of theta squared, and it's d theta on the outside. You work all this out. Now if it didn't work out so nice, you would just run the integral program and get the answer. But this one is going to work out if you just stick with it. Square everything out, combine some terms. This factors, this right here factors back to this, and then you see that cosine squared plus sine squared is just 1, and the square root of 1 is 1. So it just all boils down to 0 to pi 1 d theta. Integral of that is theta from 0 to pi, which is pi minus 0, which is pi. So So that's the arc length around the circle. Now, of course, this is a radius 1/2 circle. So it should, and it does have circumference 2 pi r, but the radius is 1/2, so 2 pi 1/2 is pi. So it totally checks out the way it should.